All right, so yesterday we looked at substitution reactions, and we said there's two different options for a substitution reaction. The first one is where your leaving group pops off, gives you a carbocation intermediate, and then your nucleophile will add into that carbocation. We said that that's a two-step reaction. The first step is rate limiting because you're going through a high energy intermediate. And therefore, the concentration of the nucleophile has no impact on the overall rate. The nucleophile is not involved in that rate limiting step. Compared to option 2, where we had the nucleophile attack in and kick off the leaving group, that was a one-step reaction. In this case, the concentration of the nucleophile does matter. Therefore, if you change that concentration, it will impact the overall reaction rate. Experimentally, this is one of the easiest ways to determine Sn1 versus Sn2. The question, though, is what if we don't have the ability to run an experiment? What if we're looking at a problem on paper? And that's where we jumped into the role of the electrophile. And we said, if we're looking at an Sn1 reaction, the key thing you're looking for is the stability of your carbocation intermediate. So we had these two examples. We had example A, where we formed a primary carbocation intermediate, and example B, where it was tertiary. And we said that example B would be way more likely because tertiary carbocations are more stable. And that led us to this trend where we said more stable carbocations increase the probability of an Sn1 reaction taking place, where you go through that carbocation. Sn2, on the other hand, we don't go through any sort of carbocation intermediate. Instead, the nucleophile attacks directly, in which case you want that carbon to be the most accessible carbon possible, right? You don't want it to be blocked or hindered in any way. So the opposite trend is true. Methyl groups are a lot more accessible than primary groups, which are a lot more accessible than secondary carbons, which are a lot more accessible than tertiary carbons. So they're opposite trends. All right. And then the last thing we finished up with yesterday was looking at an example Sn1 reaction, and we were investigating stereochemistry. So like I was saying with Sn1 in this example, it allows you to have a tertiary carbocation. It's pretty stable, at least relatively stable. So that iodide will fall off first, give you a trigonal planar carbocation. One important thing to remember is the hybridization when we started out was sp3. What's the hybridization here? sp2. So when that leaving group falls off, we undergo a change in overall hybridization and a change in geometry, right? So the original molecule was tetrahedral, but when that leaving group pops off, it's trigonal planar. You've got a p-lobe sticking up and down, which means your nucleophile can attack the top face or the bottom face, and you end up with a mixture of different stereoisomers. We did say that there is a slight preference towards inversion, meaning that that bottom lobe is slightly blocked by the leaving group that recently fell off of that face, right? So the chloride would prefer to attack from the opposite face. All right, now we've got to dig into Sn2 reactions. And these are also kind of tricky, but we have to pay attention to stereochemistry. So we're going to look at two potential options for an Sn2 reaction. With an Sn2 reaction, the nucleophile attacks straight in. We don't go through any sort of intermediate. So I'm going to draw an example here. We've got an ethyl group sticking out. Bromine right here, got a hydrogen back here, and I've got a methyl group right here. All right, in this example, I've got a nucleophile with a negative charge. So one option would be for the nucleophile to attack the front face, essentially the face where the leaving group's coming off, and then kick off that bromine. And let's imagine what this transition state looks like, right? So the transition state's the state in which bonds are being made or broken. So if we were to draw the transition state for this, we would show a half-made bond with our nucleophile and a half-broken bond with our leaving group. So let me draw the rest of it in. Okay, if our leaving group's falling off, I'd show this as a dash. And if our nucleophile is making a bond, I would show that as a dash as well. Are there any partial charges in this transition state? Partial negatives. Yeah, partial negatives, right? The nucleophile was full negative. It's halfway between being a full negative and being neutral, therefore it would be partial negative. And the bromine in this situation is halfway on, halfway off. That means it too would be partial negative. And then we can show our final product. Okay, so our final product would now have our nucleophile attached, and our leaving group completely off. So this is one potential reaction pathway for an SN2 reaction. All right. What we need to do, though, is come up with some sort of alternate example. So I'll give option B, and then we'll determine which one is more likely. All right. In this example, we're going to use that same starting material. I'm going to have an ethyl group down here, my bromine over here. Still a generic nucleophile, but this time instead of attacking the same face as the leaving group, it's going to go around back, hit the back of that carbon, and then kick off that leaving group. So now we can show a different transition state. In this one, the nucleophile is over here. It's going to attach to that central carbon. And then our bromine is going to be halfway on, halfway off. And just like with the other example, we're going to have partial negatives on our leaving group and a partial negative on our nucleophile. And our final product will have our nucleophile over here. Our methyl group down here. And then our ethyl group over here. And bromide would be our leaving group. All right, so we've got two potential options, right? One is the front face attack, one is the backside attack. Which one do you think is more likely? Backside, why? If you think about charges that are similar, they do not want to be near one another. If we look at this top one, we're running into a situation where these two negative or partial negative charges, are right next door to one another. According to Vesper theory, we know that electron-dense clouds want to be far apart from one another, not in close proximity. So this is less likely. So I'm just going to go ahead and put a big X through this arrow and say option B is going to be a lot more likely than option A, and we know that according to Vesper theory, right? Additionally, we can actually test this. What's the relationship between the top molecule and the bottom molecule? They would be enantiomers, right? So what you can do is you can actually check for optical rotation and ensure that you are getting the correct enantiomer, right? In which case, experimental data does support option B, indicating that a backside attack takes place because we know that the final product we get matches the expected optical rotation. It's kind of a cool way of checking all of this.
So attacking where the bromine is more impactful than where two carbons are here?
So
the two carbon chain, so like wouldn't that be have more of a space impact?
So that's a good question. If we look at the sterics of option A and option B, they're entirely the same. The carbon that we're attacking is equally crowded in both situations. However, that transition state for option A, we're forcing two partial negatives in near proximity. That's a lot less likely than doing a backside attack. All right, so this is the true overall reaction mechanism for an SN2 reaction. What do we call this sort of geometry? Assume that the bond to the nucleophile is a real bond. Yep.
I had a question before that. So which one is more important, sterics or the transition state, or the opposite? Like,
so in this example,
this one's the same.
Yeah. If you're looking at a reaction, it depends, right? So this carbon that we're looking at is a secondary carbon that can actually do SN1 or SN2, and we'll cover tiebreaker rules later. It's kind of this middle gray area, right? Primary in methyl prefers SN2, tertiary in resonance prefers SN1, secondary, it can go either way, right? All right, so if we think about this transition state, it's got a unique geometry. What's this geometry? Trigonal bipyramidal. So we call this a trigonal bipyramidal transition state. Okay, so that's a really important thing to remember. Another way of describing this reaction is almost like an umbrella flipping inside out. So if you've ever been outside on a windy day, your umbrella could flip inside out. It's a similar sort of reaction. This is referred to as an inversion of configuration. So Sn2 reactions experience an inversion, meaning when you go through that trigonal bipyramidal transition state, what was originally facing the left essentially goes planar and then flips to the right. So we do experience that kind of flipping inside out. Does that make sense? It's kind of confusing. All right, so what I want to do now is, if you have that chart with you, we're going to start filling in that chart. It's a really good way of organizing your thoughts and rationale. I might have to just do it on scratch paper if somebody else grabbed too many. Sorry. If you don't have a copy of it, just do it on scratch paper. It's okay, and then transfer it over. All right. So I really like having this kind of consolidation of ideas onto one common sheet. Let's compare the mechanism for an Sn2 reaction and how it differs from an Sn1 reaction. So if you think about an Sn2 reaction, is it one step or two steps? One step. So it's a one-step concerted reaction. Another way of describing this is that the nucleophile shoves off the leaving group. Right, so that nucleophile slams into that carbon and kicks off the leaving group. Sn1 reactions, like we said, are stepwise. And we said that the leaving group falls off first. That results in a carbocation. It's important to remember, if you have a carbocation and it can rearrange into a more stable carbocation, it will, right? So that's something you always have to pay attention to anytime you're doing an Sn1 reaction. All right, the rate equation. The rate equation for an Sn2 reaction should be bimolecular, hence the 2. So it's going to be rate is times some sort of K, that's our rate constant, times the concentration of our nucleophile. The nucleophile could have a negative charge or no negative charge. We'll talk more about that next. And then we also need the thing with our leaving group, so I'll call that our substrate. That's the thing being attacked by the nucleophile. An Sn1 reaction is unimolecular. So we've got rate times a K times the concentration of our substrate. So like I said, a really easy experimental way to check is to double the concentration of your nucleophile. If the rate doubles, you know it's Sn2. If it doesn't double, it indicates that the reaction's Sn1. All right, stereochemistry. For Sn2, we just said that when the nucleophile attacks, it attacks from the back face and actually flips that carbon essentially inside out. So you experience an inversion of stereochemistry. All right, with Sn1, do we only get one product? No, you can get more than one product, so you can get a mixture of stereoisomers. All right. However, there is a preference for inversion as well for this one. All right. So stereochemistry for Sn2, you get one product. For Sn1, you might get more than one product, assuming you're making a stereocenter. All right, substrate, the electrophile. So that's the thing that we're attacking with our nucleophile. For Sn2, what's more favorable, a bulky one or a less bulky one? Less bulky. So that we can clarify this and we can say sterics impact rate. So we'd say methyl is better than primary, is better than secondary, which is way, way better than tertiary. So much so that tertiary carbons, for the most part, really never ever do Sn2 chemistry. You only ever see it with methyl primary and sometimes secondary. All right, with Sn1 reactions, the story is a bit different. It's not sterics that we're concerned with. Instead, it's carbocation stability. And we know from experience that resonance is the best, which is better than a tertiary carbocation, which is better than a secondary, which is better than a primary, which is better than a methyl. And again, just like with the other example, primary and methyl carbocations are so ridiculously unstable that we almost never see them with Sn1 reactions. The only time you might see a primary carbocation in an Sn1 reaction is one in which it's resonance stabilized. Resonance trumps everything, right? So if it is a resonance stabilized primary carbocation, it can do Sn1. All right, so now what we need to do is we need to kind of start exploring the nucleophile. If you've noticed, all of the nucleophiles I've been using, I've just been writing NU. That's not a real thing. We got to be a little bit more clear. All right. So the role of the nucleophile does get confusing, but you got to bear with me. All right. So let's take a look at Sn1 reactions first, and then we'll do Sn2 second, just like we've been doing with the other things. And again, I really like comparing reactions for each of these. So we'll have reaction A compared to a reaction B. So for example, in this reaction, what we're going to do is have a tertiary carbon with the leaving group. We know that's way more likely to do an Sn1 reaction than an Sn2, right? Because it'll go through a stable carbocation. And in this, what we'll end up doing is we'll react this with an iodide down here. And for B, we're going to do the same thing. However, instead of an iodide, we're going to react it with a bromide. Okay. So what's the first step? Leaving group falls off in each situation. So if we do that, our iodide is now next door, plus our leaving group with a negative charge. Same thing down here, but with the bromide. And then the next step, we said our nucleophile is going to attack in. Do we have to worry about making stereoisomers here? So let's check. My iodide attacks in. Have we created a stereocenter? No, so we don't need to worry about a mixture of stereoisomers in this example because we don't even have a stereocenter to begin with. So that does happen sometimes with Sn1. And then our leaving group is just going to hang out on its own. Same thing with this one, no stereocenters. Got bromine attached now, and we've got a leaving group. All right, do you think the rate is going to differ for either of these reactions? What's the rate limiting step? The leaving group falling off. So the rate for these are going to be near identical, right? Because In this case, we're going to assume the leaving groups are the same. If that's the rate limiting step, it's the exact same step for the top reaction as the bottom reaction. All right. However, there's still more going on. What I want to imagine is which of these nucleophiles is more aggressive with attacking that carbocation. So let's stop and think about that. Which nucleophile is less stable, whoops, and therefore more aggressive with attacking the carbocation? What do you think? So you think bromide is less stable? Why? It's a smaller atomic size. Yeah, so bromine is less stable. So Br minus is less stable due to atomic size. And is therefore a better nucleophile. However, like I said, if we look at both of these reactions, does that mean reaction B is going to be faster than reaction A? No. The strength of the nucleophile doesn't impact the rate limiting step. The rate limiting step for this reaction simply involves that leaving group falling off. So the nucleophile, yeah, we can look at it. It just doesn't really tell you a heck of a lot with an Sn1 reaction. So that's going to be my third note. So I'm going to write, however, in all caps. The nucleophile strength really does not matter. Since the rate for Sn1 does not include the nucleophile. All right, so these are pretty important concepts that we're considering. We always have to piece together different options and compare them. In this case, yeah, we came up with competing hypotheses, but we don't really have any sort of evidence that one will be faster than the other, right? So nucleophile strength doesn't really impact a whole heck of a lot with Sn1 reactions, which is confusing for people. There is another aspect to this too that even gets more confusing. You ready for that one?
No.
Can I just get a bottle of iodide and sprinkle that into a reaction? No, I've got to have solvent too. Solvent will change things. We're going to leave that on the back burner for now and come back to it a little bit later. All right, so Sn1 reactions. The main thing to take away from that is that the nucleophile strength doesn't really matter. In fact, a really, really weak nucleophile does a perfectly fine job. As long as you've got some lone pairs to donate, you can do Sn1 chemistry. So I'll write down weak nucleophiles work just fine for Sn1. All right, let's do Sn2 reactions now. Sn2 reactions are where the fun begins. All right, so let's do the same thing with an Sn2 reaction. We've got a primary carbon. Did I do iodide first? I'm trying to remember. Yeah. All right. Whoop. It should be Br minus. All right, so in the first one, what we've got is a nucleophile that can attack the backside, kick off the leaving group. Just like we said, it's going to attack the backside of that carbon. So I like to show that with my reaction arrow. Do the same thing with bromide. Kick off the leaving group. And now we've got I minus. Oops, sorry. The iodide has attacked, and the leaving group is leaving group minus. Then for the bottom one, I'll have leaving group falling off with a negative charge. All right, looking at this reaction, does the nucleophile matter? Yeah, it's a part of the rate equation. Which reaction would you expect to be faster? Br minus, right? Br minus, you're forcing that negative charge into a smaller atomic cloud, right? So it's going to force it into a more compact area. Negative charges prefer room to roam, right? So if I'm a negative charge, I would prefer to be in a gigantic iodine electron cloud than a tiny, or I shouldn't say tiny, a relatively small bromide cloud. So in this case, this is less stable. And therefore a better nucleophile. And I am going to put an asterisk down here, and I'm going to write solvent can affect this. We're going to ignore that for the time being, and then we'll kind of throw that in later. Yep.
So are you saying that in specific solvents, iodide could be a better?
Yes. In some solvents, iodide is actually a better nucleophile than bromide. It's confusing, but we're going to cover solvent completely separately. Right now, we're just kind of ignoring solvent altogether, and we're saying which ion is more stable or less stable. The less stable ion is going to be less happy and therefore more aggressive about attacking that carbon. Yeah?
Is the fact that the bromine is also, like, not only is it smaller, so it's less stable, but also it's smaller, so it can, like, sneak in to the substrate?
Yeah, so that's the next thing we're going to look at is what effect does size have. In this case, another argument could be made that bromide's smaller. It's going to have an easier time sneaking into that carbon and attacking it, right? So I think that's a really fair claim. All right, so let's make a note on this one. So reaction A will be faster, assuming that we ignore solvent. Oh, shoot, reaction B. Whew. Thank you. This is why I keep you around. All right, so reaction B is faster because it has the less stable ion. If you go back to that acid-base chapter, we talked all about stability of anions. This is coming back again, right? So we can use those same cardio rule trends that we used in acid-base chemistry to compare the relative stability of these anions as nucleophiles. It's kind of handy. All right. Now let's compare a different one. So example 2. And this again is going to be an Sn2 reaction. All right, and in this Sn2 reaction, I'm going to have reaction A with a leaving group attached, reaction B with a leaving group attached. Reaction A, my nucleophile is going to be ethoxide, so it's ethanol that's lost its proton. And in the bottom one, I'm going to have tert butoxide. All right, so same idea. This is going to be our nucleophile, attack the backside of our substrate, kick off our leaving group. What new functional group have we made? We've made an ether in this situation. This is an actual named reaction, your first named reaction of organic chemistry. This is the Williamson ether synthesis. Pretty simple Sn2 reaction. So you can use this to make a whole wide variety of different ethers. All right, and then we've also kicked off our leaving group. And let's do the bottom one as well. Same idea. this off. And we've kicked off our leaving group. All right? So my next question is, which reaction is faster? Another way of asking this is, which is the better nucleophile? So raise your hand if you think A is the better nucleophile. Raise your hand if you think B is the better nucleophile. This is great. Why is A the better nucleophile? It's smaller, right? If you're trying to attack something, you don't want to carry a bunch of garbage hanging off your back, right? You'd rather be tiny and compact like a ninja and sneak in there. All right, so reaction A will be a lot faster. Smaller and more compact. Or actually smaller and actually I'm going to change this. Smaller or less sterically hindered. All right. This does get confusing for people though, and I'll show you why. So let's go back up and look at this one. Up here, we looked at the stability of the anion as our nucleophile. We said the less stable it is, the more nucleophilic it's going to be, and that we could follow those cardio rules that we had been talking about. Down here, if we look at these, we could say, well, which nucleophile is more stable? They're about the same stability. Oxygen with the negative charge, oxygen with the negative charge, no resonance, nothing like that going on. So these are approximately the same stability, but we do have to factor in sterics. So when we're looking at a nucleophile, we really have to look at two things. We have to look at sterics and stability. They're two very important things. With bases, we didn't really look at sterics at all, right? And they're very different because of that. So let's make a note. With nucleophiles, you must consider stability and sterics. In fact, if your nucleophile is super duper bulky, it's just never going to be a good nucleophile. So in this example, the terp butoxide anion is kind of a crummy nucleophile. It's just not going to go very fast, and in some cases won't do substitution at all. Yep.
So if you compared that, the second one, the deprotonated like ethanol, which still has 4 carbons, but they're in a line instead of kind of grouped up.
Yeah. So the question was, what if instead of it being a terp butyl branch right off of that attached carbon, what if it's a longer butanol chain, like a straight chain butanol? That's probably going to be more similar to the ethoxide anion than the terp butoxide anion, because the bulk is spread out and further away from the site doing the attacking.
So it's not necessarily how heavy it is, it's the bulk is like at one.
Exactly. It's not the overall mass, it's just the bulkiness right around that anionic center. Great question. All right. So it is a little bit weird. If you're comparing up and down a column, what determines stability? Atomic size. What if you're going left and right across a row? Electronegativity. So make sure you do remember a lot of those trends from our acid-base chemistry section. All right. So I gave you a handout that talks about relative strength of the nucleophile. And unfortunately, it's not color-coded because it's TCC and we aren't allowed to print very much in color. But you can highlight them if you want. So this is kind of discussing, all right, if they have really similar trends to basicity, why on earth are they different, right? And we already talked about that briefly. We said with nucleophilicity, you need to consider sterics, not just stability, right? So that's one different with nucleophilicity and basicity. However, they're pretty similar in many respects. So let's take a look at how they're related. So if you have a base, the base is going to attack that proton. So in many ways, your base is your nucleophile. It's going to attack your proton as an electrophile and kick off your leaving group. And in this case, the leaving group with the negative charge is going to be your conjugate base, right? So it's similar type of electron arrow pushing. Versus an Sn2 reaction shown below, your nucleophile will attack that carbon and kick off your leaving group. In this case, your leaving group's just a leaving group. We don't call it a conjugate base anymore. So pretty different. All right. So it says nucleophilicity is a measure of kinetics. So nucleophilicity, what we're looking at is reaction rate, where basicity is a measure of thermodynamics. So what do I mean by kinetics? Reaction rate. How do we look at reaction rate if we're looking at a reaction coordinate diagram? It's that hill you have to climb, right? So nucleophilicity, we're looking at that hill you have to climb. Is it a really hard hill to climb, or is it a really short hill to climb? Basicity says, I don't care about the hill. I just want to know where I'm going to end up, right? So it's saying, I want to look at that drop, that delta G change. All right? So if we look at number 1, it says better nucleophiles, the red curve, react more quickly than less nucleophilic reagents, which are the blue curve. So you can see the blue curve has a much greater activation energy. Its hump goes all the way up like that, versus the red one has a relatively low activation energy compared to the green one. What about their delta G values? They're the exact same thing, right? So in this case, there's no difference in delta G. We only cared about the difference in activation energy. So another good way of thinking about this is, you remember that ethoxide example where we had ethanol that was deprotonated and terbutoxide? The delta G for that reaction would be roughly the same. Not a big change in delta G for either reaction, meaning your products that you're making are about the same stability as each other. However, we said that one of them was sterically a lot more bulky, meaning it's going to be a lot harder to orient itself and to attack that carbon. Therefore, it's going to have a much higher activation energy. That's going to slow down the reaction rate. All right. And then basicity. Basicity, like I was saying, we don't care about the activation energy. All we're looking at is that drop in Gibbs free energy. So in this case, the better base is shown in red because it has a bigger drop in Gibbs free energy, meaning it's forming more stable products in that reaction. However, the blue base, or the blue curve, shows a worse base that has a smaller drop in energy, but in this case, the activation energies were about the same for each of them. The interesting thing with acid-base reactions is, if you think about a base, right? A base is trying to pluck off a proton. It's not that hard to pluck off a proton, so the activation energy is pretty small and insignificant, so we don't worry about the activation energy for acid-base reactions very much. We do worry about it with a nucleophile attacking a carbon, because it's two potentially sterically bulky things running into one another, right? It's not just like plucking a proton off. So it is kind of different. It's a fine distinguishing feature between the two, but it's a really important distinguishing feature. All right. So what I want to do is, again, go back to our decision-making chart, and we're going to fill in a little bit more about the nucleophile. All right, for an Sn2 reaction, what nucleophiles are the best? It's better if they're unstable, right? And we said the other half of this is it's better if it's not bulky, right? You don't want a bunch of spinach hanging off of there, as my old advisor used to say. All right, Sn1 reactions. We said, yeah, the nucleophile, you can use a stronger or weaker one. Doesn't matter, though. It just doesn't impact the overall reaction rate. So you can get away with using a really weak nucleophile for an Sn1 reaction. And often I will say that these are usually weak. And in fact, we're going to talk about why they're usually weak when we get into our next chapter. But oftentimes, if you have a strong nucleophile, it's also a strong base. And so it might do acid-base chemistry in an Sn1 reaction rather than a true Sn1 reaction. So we'll talk about that when we get to the next chapter, but don't worry about it for right now. All right, I'm hoping I still have Wi-Fi. Yes, I do. Are you ready for the best videos in the world? Oh no, I gotta plug it in.
General alkanes undergo acid.
All right, here we go.
Primary halogen-alkanes undergo Sn2 reactions, where the S denotes a substitution reaction. The N shows the reaction involves a nucleophile. 2 is the number of species involved in the slowest rate determined step. A nucleophile is an electron pair donor. It is attracted towards species carrying a full or partial positive charge, with which it can form a dative covalent bond. Consider the reaction between a hydroxide ion in solution and bromoethane. Both reactants are involved in determining the rate of the reaction in a one-step process. The hydroxide ion attacks the carbon atom from the opposite side to the halogen atom, because the bromine atom, A, is so large it impedes the approach of the smaller hydroxide ion, and B, it repels the negative charge nucleophile. The lone electron pair on the nucleophile forms a new dative covalent bond with the partially charged carbon atom to give an unstable transition state complex. The complex behaves like an umbrella blown inside out as the bonds rearrange into a tetrahedral structure. A bromide ion, called the leaving group, is released.
I smell an Oscar. Do you want to watch the next one? I don't know, but I really like it, and I don't know why, but I figured I'd share it.
It is a good visual.
It is a good visual, right?
Tertiary halogen-alkanes undergo Sn1 reactions, where S indicates a substitution reaction is occurring, N indicates that a nucleophile is involved, and 1 indicates that only one species is involved in the slowest rate determined step. In tertiary halogen-alkanes, the small hydrogen atoms in primary halogen-alkanes are replaced by bulkier alkyl groups. The bulky alkyl groups do not allow attacking species to approach the central carbon atom. Consider the reaction between 2-methyl 2-bromopropane and a hydroxide ion. It has a two-step enthalpy profile. The first step, the heterolytic fission of the carbon-bromine bond, has a high activation energy, EA1, and therefore determines the rate of the reaction. The first step involves only the halogen-alkane and proceeds via a transition state complex to form a carbocation. The second step has a much lower activation energy, EA2, and hence is considerably faster than the first step. The carbocation reacts with a nucleophilic hydroxide ion via a second transition state to form the product 2-methyl propane 2-ol. Transition state. Carbocation.
And remember, if you have a carbocation, it can also rearrange. That's kind of the curveball that's thrown at you with Sn1, but you don't have to worry about it with Sn2. All right, I think that's where we'll leave it. Make sure that you do practice a lot in this chapter because there's a lot of different variables you have to pay attention to.